Determining the formula for a compound. There are two types of formulas that we're going to be dealing with in this section. The first type of formula is called an empirical formula. And the empirical formula is the simplest whole number mole ratio of atoms in a compound. So to look at a few examples, CH is an empirical formula because it's got a 1-to-1 ratio of carbon to hydrogen. CH4, which is known as methane, has a 1-to-4 ratio of carbon to hydrogen, which is the simplest ratio. CH2O is a 1-to-2-to-1 ratio. And K2CR2O7 is the simplest ratio of potassium to chromium to oxygen. So all of these are examples of empirical formulas because they're the simplest whole number ratio of atoms in a compound. Now molecular formulas are another type of formula we're going to deal with in this section. And when we look at molecular formulas, they are the actual ratio of atoms that are in a compound. Sometimes the molecular formula is the same as the empirical formula. So the compound is found in nature in the simplest whole number ratio. But sometimes the actual ratio of atoms is not in its simplest form. It may be some multiple of that form, and that would be our molecular formula. So again, if we look at some examples, C6H6 is a molecular formula. It's the actual ratio of carbon to hydrogen in the compound called benzene. But it's not the empirical formula for benzene because 6 to 6 can be simplified. The empirical formula for benzene, the simplest whole number ratio, would be CH. Now CH4 is the molecular formula for methane. Methane comes in a 1-to-4 ratio of carbon to hydrogen. But it's also the empirical formula because it's the simplest ratio. C6H12 is the molecular formula, or the actual ratio of carbon to hydrogen in hexane. But it's not the empirical formula because it's a 6-to-12 ratio. The empirical formula for hexane would be CH2. And K2CR2O7 is the molecular formula for potassium dichromate. It's also the empirical formula because it's in the simplest whole number ratio. So let's determine the empirical formula and then eventually the molecular formula of a compound from data in lab. So let's say we're looking at rocket fuel. And we're told that rocket fuel is 87.4% nitrogen and 12.6% hydrogen by weight. Mass analysis also tells us that the molar mass for this rocket fuel is 32.05 grams per mole. We first want to find out what the empirical formula is, and then we want to determine what the molecular formula is. So the things we're going to do. We're going to assume that we have 100 grams of the compound. It's a ratio, so we could assume any amount. But if we assume we have 100 grams of the compound, the percents by mass for each of the elements in that compound will be the same as their masses. The second thing we're going to do is take the mass of each element in the compound and convert it to moles. And our last step will be to find the simplest whole number mole ratio of atoms in the compound. That will give us our empirical formula, and then we'll have to find out how many times greater our molecular formula is from our empirical formula. So let's go back to the problem. Okay, we have nitrogen and hydrogen in our compound. So let's start with nitrogen. It told us that we had 87.4% of the compound is nitrogen, and if we have 100 grams of the compound, we have 87.4 grams of nitrogen. We can convert that to moles. 1 mole of nitrogen is 14.01 grams of nitrogen. Now we had 3 significant digits in our given number, so we'll write our answer with 3 digits, and that'll give us 6.24 moles of nitrogen. We're going to do the same thing with hydrogen. It told us we had 12.6% by mass of hydrogen in the compound, so in a 100 gram sample, we have 12.6 grams of hydrogen. The periodic table tells us that 1 mole of hydrogen is 1.01 grams of hydrogen. We'll plug that into our calculators, round off to 3 digits, and that'll give us 12.5 moles of hydrogen. Now we wouldn't write our compound as N6.24, H12.5. We want to come up with the simplest whole number ratio. And the easiest way to do that is to divide by the smallest number. So we're going to divide by 6.24 and 6.24. That's going to give us a 1 to 2 mole ratio of nitrogen to hydrogen, and that's our simplest whole number ratio. So our empirical formula is N1, which we'll assume, H2. Now the next thing we want to do is we want to find out what the molecular formula is. The empirical formula is the simplest ratio. The molecular formula is some multiple of that. So if we look up NH2 on the periodic table, we've got 1 nitrogen times 14.01. We've got 2 hydrogens times 1.01. And that's going to give us 16.03 grams per mole for that empirical formula. Well, it told us in the question that this particular compound has a molar mass of 32.05 grams per mole. So if we take 32.05 and divide it by 16.03, that's going to give us 2. That means that our molecular formula is twice our empirical formula. So N2H4 would be our molecular formula. Okay, so we need to go back and erase this. All right, so let's look at another example of an empirical formula problem. We're going to look at deadly nerve gas, which contains carbon, hydrogen, oxygen, phosphorus, and fluorine. So it's got more work, but it's the same basic problem. And it also tells us that the molar mass for the compound is 184.1 grams per mole, so that'll help us to determine what the molecular formula is. So we're going to do the same steps that we did before. We're going to assume that we have 100 grams of the sample. And if we have 100 grams of the sample, that means that our percents equal our masses. So our first element in our compound is carbon. So we've got 39.10 grams of carbon, which we're going to convert to moles. So 1 mole of carbon is 12.01 grams of carbon. We'll plug that in. We'll get 3.26 moles of carbon. Then for hydrogen, we have 7.67 grams of hydrogen. We'll convert that to moles. So 1 mole of hydrogen is 1.01 grams of hydrogen. So that'll give us 7.61 moles of hydrogen. For oxygen, we have 26.11 grams of oxygen. And we'll divide that by the atomic mass for oxygen. That'll give us 1.63 moles of oxygen. We've got phosphorus, 16.82 grams of phosphorus. 1 mole of phosphorus is 30.97 grams. So that'll give us 0.543 moles of phosphorus. And then for our last one, we have fluorine, which is 10.30 grams. 1 mole of fluorine is 19.00 grams of fluorine. So that'll give us 0.543 moles of fluorine. Again, those numbers aren't whole numbers, so our next step is going to be to divide by the smallest number. So we're going to divide by 0.543, and we want to keep the ratio the same, 543, 0.543, 0.543, and 0.543, and that's going to give us a 6 to 14 to 3 to 1 to 1 ratio. So our empirical formula is C6H14O3PF. Now when we look this up on the periodic table, that gives us 184.1 grams per mole, which is the same as the molar mass for the compound. So for this particular example, our empirical formula and our molecular formula are the same.